Deep learning excels at interpreting images and text, but when fed structured mathematical topologies, standard models can experience a critical failure of machine perception. They can go completely blind. Let's look at two distinct graphs. On the left, we have two disjoint triangles. On the right, a single hexagon. They share the exact same number of nodes and the same degree per node, but their physical structures are entirely different. We feed both structures into a message-passing graph neural network using mean pooling. Each node gathers neighbor features, averages them, and updates its state. We then plot the final vectors into a latent space. Both structures collapse, landing on the exact same coordinate. The network produces an identical mathematical representation for both graphs. It cannot tell them apart. The neural network is mathematically blind to the specific topological differences between these two inputs. To understand why this happens, we have to step outside of deep learning and look at discrete mathematics. Specifically, we need to ask how classical, non-neural algorithms test if two graphs are structurally distinct. We will examine a classical heuristic called the one-dimensional Weisfeiler-Lehmann test. By understanding how this test works, we can map the strict theoretical limits of message-passing networks and then derive an architecture designed to hit that absolute ceiling. If a model cannot distinguish a hexagon from two disjoint triangles, it cannot accurately model complex molecular bonds or financial transaction networks. Solving this structural blindness is a strict prerequisite for deploying graph representation learning in the real world today. The benchmark for testing graph isomorphism is the one-dimensional Weisfeiler-Lehmann test, also known as naive vertex refinement. This algorithm starts by looking at the raw features of every node in a graph. It maps those raw features to a unique starting color, which we denote as CV sub 0. Next, the root node looks at its direct neighbors. It collects all of their current colors and groups them together into a mathematical multiset. The algorithm then takes the root node's own color plus this new multiset of neighbor colors and passes both inputs into a hash function. This hash function is strictly injective. That means every single unique combination of inputs must produce an entirely unique, non-colliding output color for the next step, CV sub 1. You repeat this process across the entire graph for L iterations. If you compare two graphs and find that their final sets of node colors are different, you have mathematically proven the graphs are non-isomorphic. But it is a heuristic. If the final color sets between two graphs remain identical, the test fails to distinguish them. This brings us to a formal proof known as Theorem 5.2. It establishes that a standard message-passing graph neural network is at most as powerful as the 1WL test in distinguishing graph structures. Looking at the two side by side, the message-passing network is architecturally a continuous, differentiable analog of the 1WL test. It replaces discrete colors with continuous vectors and replaces the hash function with message, aggregate, and update layers. So if a neural network is going to match the 1WL test's expressive power, Theorem 5.3 dictates that its internal operations must collectively form a strictly injective mapping over the neighbor features. If it fails to do this, the network will inevitably map different structural subgraphs to the exact same vector. Our network collapsed a hexagon and two separate triangles into the exact same latent space. To figure out why, we need to locate exactly where our network broke the rule of injectivity. So, what specific mechanism inside a standard graph convolutional network causes it to violate injectivity? It comes down to how the network handles a multiset. Remember, a multiset is a set that allows repeating elements, which is necessary because a node will often have multiple neighbors sharing the exact same features. To process these neighbors, networks use invariant pooling, an operation designed to process elements regardless of what order they arrive in. Let's test max pooling. We have two distinct multisets. S1 contains a 1, another 1, and a negative 1. S2 contains just a 1 and a negative 1. The maximum value for both sets is exactly 1. Because it outputs the exact same scalar for two different inputs, max pooling fails injectivity. What about mean pooling? Let's use two new multisets. SA contains two identical feature vectors, C and C. SB contains only one C. Mean pooling captures the distribution of features, but it destroys the exact element counts. The average of C and C is C. The average of just C is also C. It averages out exactly the same. Both standard pooling methods explicitly erase the multiplicity of elements. By deleting exact neighbor counts, standard pooling mathematically guarantees that the network will lack the structural evidence required to distinguish between different tautological variations. We need a mathematical operation that cures this amnesia. Let's test sum pooling on those same two multisets, SA and SB. By summing the elements, SA outputs 2C, while SB outputs just C. Sum pooling mathematically preserves exact multiplicity and resolves the collision. This aligns with Lemma 5.1, the universal approximation of multisets. It states that any injective multiset function can be constructed by applying a function phi to each element, summing those results together, and then applying an outer function. Because multi-layer perceptrons act as universal approximators, we can directly implement this lemma inside a neural network. We can now build a highly expressive architecture known as the graph isomorphism network, or GNN. We start our node update rule with the strict sum of its neighbor representations. Next, we add the root node's own representation to that sum, but we modify it with a learnable scalar parameter, 1 plus epsilon. Epsilon ensures that the root node's data is weighted differently than its neighbors. This prevents any internal feature collisions, maintaining strict injectivity within the node's own local structure. Finally, we wrap the entire mathematical expression inside a multi-layer perceptron. By swapping a destructive mean function for a strictly injective sum pool, the graph isomorphism network successfully reaches the absolute theoretical expressive ceiling of the 1WL test. To prove it, we will run our initial graphs, the two disjoint triangles and the single hexagon, through our new architecture. As the message passing iterates, the network executes sum pooling. The exact neighbor counts and local structures are flawlessly preserved. We project the outputs back into latent space, and this time they aggressively diverge. They land on two entirely distinct coordinates. The collision is solved. We have engineered maximum expressive power for a standard homogeneous graph. But our entire mathematical derivation rests on a single assumption, assuming every node and edge in the network is functionally identical to the next. In real-world data, a node representing a person does not behave like a node representing a bank account. What happens to the theoretical limits of message passing when the graph structure itself becomes heterogeneous?